Okay, so now let's proceed to create our first flow sheet. From now on, you will learn how to build a flow sheet, run the simulation, and view the results. And how we will be learning that. I'll use some real-world examples so you can get a better idea on how we use a simulator to solve our daily problems. Okay, so the task one includes some simple calculations. So imagine that someone came to you asking, what is the viscosity of water at 75 degrees Celsius? And what is the vapor pressure of water at 50 degrees Celsius? Can we calculate that in the DWSIM? Yes, we can. So let me show you how we can do it. I'll open the classic user interface and I will create a new simulation. This is the simulation configuration wizard. It lets you set up a new simulation in a very easy way. Okay, you can close it, but just for now we will use it. The first thing you must do to set up your simulation is to add the compounds you will need on your simulation. In this case, we will need only the water compound. You can select it from this list. You can search for its name, as I did, and after selecting it, you should click on Add. And on this box, you will see a list of added compounds. In our case, only water. Okay, so you can click on Next. Now you should select your model, your property package, which is a set of models and methods to calculate properties of the objects in your simulation. Okay, in our case we will use the steam tables property package, which is a package which includes only methods and procedures to calculate water properties, water and steam properties from experimental data. Okay, so we will add a copy of this property package. Next. And the flash algorithm in this case is irrelevant because the steam tables property package already has its own methods to calculate equilibrium between liquid and vapor phase. Okay, so we can just let this selected on nested loops, but it won't be used in our simulation. Now we can select the system of units for our simulation. You don't need to change this now. For now we will let it selected on the default units, which is the international system. We'll click finish. So going back to our question. First question, what is the viscosity of water at 75 degrees Celsius? How can we calculate that? You can see on this right side of the window, we have a list of objects that we can include in our simulation. The object that includes material and its properties is the material stream. We can select and drag one of it to the flowsheet area. So this is our material stream. I will explain it how it works later and what is its role in our simulation. Okay, but for now let's just focus on calculating our property. You can see that it is already calculated because it is already defined with default properties. It has a mole fraction are equal to 1 for water, because we only have water. Okay, and we have a default temperature and default pressure. And to calculate our property at 75 degrees, you can type 75, change the units of the temperature to Celsius, and it will convert automatically to Kelvin. You can see that the stream was already calculated, and you can go to phase properties. You see that at these conditions the stream is only liquid. Okay, and if we click on the liquid one tab, we can scroll down to the bottom of the list, and you will find the viscosity of water. If you don't like this unit, you can change it here. Go to Edit, Simulation Settings, go to System of Units, and create new. You can give you a name to your new system of units. I'll type 9 units. I'll choose Celsius for temperature, bar for pressure, and centipoise for dynamic viscosity, okay, and centistokes for kinematic viscosity. We click add. It should be add here, not adicionar. Adicionar is in Portuguese. After adding your own system of units, you should select it from this list. And now everything in your simulation will be using this system. See? So this is our viscosity of water at the required conditions. Next question is, what is the vapor pressure of water at 50 degrees Celsius? How can we calculate that in the DWSIM? First, we need to change the temperature and press enter so the DWSIM can store the new value. And we can change the specification of the stream to temperature and vapor fraction. You'll see that something has changed here. You will need to specify the temperature, which we already entered here, and the phase mole fraction of the vapor phase. You should recall from your graduation classes that the vapor pressure of a single compound is the pressure where it is on the saturation condition. So in a process simulator, this is the same as saying that the material stream is with a vapor fraction of 0, which is the bubble point of the mixture, or 1, which is the dew point of the mixture. So if we want to find the vapor pressure of a single compound mixture, we can either type 0 or 1 in this box, because the bubble and the dew points will be the same. They will actually be the vapor pressure of the single compound. Okay, so if you type 0, you find the vapor pressure of water here at this box, which is 0.1235 bar. If you type 1 and press enter, you will find the same result, because, as I said before, we're dealing with a single compound mixture only. Okay, so here it is. Okay, so now let's continue with our task. I'll create an Excel worksheet because I want to compare the results from other models. Okay, let me put it here. Steam tables. I'll compare the results with the ones from the Peng-Robinson equation of state and from the Cookprop library. I'll include the Raoult's law. Okay, so our results from steam tables are this one, 0.35. Okay, so now let's see the results with the Peng-Robinson equation of state. We should go to settings, bases, remove the steam tables property package. Let me just hide this window for now. And double click on the Peng-Robinson property package. Now we can either calculate or click on solve flow sheet and it will recalculate the stream, or we can do a right click on the material stream and choose recalculate, or even select the flow sheet and press F5. They all do the same. Now let's check the value of viscosity. Is 0.54. Oh, oops, the temperature is wrong. This is the vapor pressure result, not viscosity. Let's do it again, just to get it. 0.12369. And now for the viscosity. Zero 0.3717. Now let's try the coolprop library. Go to settings, remove the PenRobson property package and add coolprop property package. Let's recalculate the stream, check the results. Almost the same, 0.377. Now for the vapor pressure. Oops, we've got an error. This is a coolprop error, not the DWSIMs. For now, we don't support T temperature below melting point. I don't know why this happened, but we can click on the more info button to see more details. Maybe something coming from the coolprop library. We will investigate this in a moment. Okay, so let's just put NA here. Now let's try the ideal property package, which is based on the Rhodes law. Settings, remove prop, and add Rhodes law property package. And let's try to recalculate this. Okay, now we've got the same value, 0.5236. And for the viscosity at 75 degrees Celsius and 1 bar. Zero 0.3717. Okay, now we can see that the viscosity values are almost the same. PenRobson and Rhodes law are the same, but the coolprop library and distinct tables have different results. So why is this happening? Let's run DWSIM in a debug session so we can see where these values are coming from. First, we will save the simulation. You should click on this button, Save Active Simulation. I'll save it to the desktop for now. Desk1. Okay, let me close the DWSIM. And I will run a debug session on Visual Studio. I'll open the simulation that we just saved. Let me see which property package we left. It's Rhodes law. Okay, so let's first try to see where this viscosity value is coming from. I'll insert a breakpoint at the code location where this property will be returned. Use on the thermodynamics library, base classes, property package. You don't have to worry about it now. This is something we will see with more details at the developer course, okay? So let's down. This is the routine that calculates the phase properties. This is the part that calculates the liquid phase properties. And this is the value of the viscosity for the Rhodes law property package. Let's try to calculate it. And you will see that the value of the viscosity is returned as 0.00037 Pascal times seconds. And this is the routine that returns the viscosity value. Let's try to go back to it. Go to definition. Okay. So what is happening here? The DWSIM tries to calculate the mixture viscosity, but since we only have one component, which is water, we will be interested in the value that this function returns. Okay, so let's see what's going on. If the reduced temperature is less than 1, then we can proceed to the normal calculation. If the compound is a petroleum fluid, then it calculates the viscosity using a different correlation, but since it is not, we will investigate from which database this compound is from. And it is from the ChemSep database. So the code will jump to this section, which calculates the viscosity from a curve with coefficients coming from the ChemSep database. The equation number is 101. So this value will come directly from a ChemSep equation, based on experimental data. So the DWSIM can send the parameter values to the routine, and it will return the value of the viscosity, which is the same that we saw earlier. Okay. Okay, so let's continue. Now let's change the property package back to cuprop and try to see where this value is coming from. You can see that the value is a little different. Let's try to catch the value that comes from ChemSep library, from the cuprop library. Cuprop phase props. Okay, here it is. Okay, but this time you will see that this value is coming directly from cuprop. The routine will go back to the main routine, but it will then call the compound liquid viscosity routine back from the cuprop instance, which is this routine. Let me try again. Here it is. Okay, so this is where this liquid viscosity is coming from. First we need to check if the compound is supported by cuprop, and water is. Minimum temperature for water, for the cuprop to return properties for water, is the fusion temperature, melting point, and the maximum temperature that cuprop supports is 2000 Kelvin. And the water critical temperature is here, returned by cuprop. And if the temperature is higher than the minimum one and less than the maximum, and it is less than the critical temperature, we try to get the viscosity from the cuprop library. And if everything goes okay, we should see the viscosity value coming directly from the cuprop library. Okay, and here it is. So this is where the viscosity is coming from. Okay, I hope this had helped you to understand where these properties come from, depending on the property package that you select in the DWSIM. Okay. Okay, just for curiosity, let's see the result that is returned from the steam tables property package. Since it is used only for water and has specific correlations for water. Let's search the code steam tables. Let's see if we can find the phase props. Phase ID 3 is liquid 3 corresponds to liquid 1 internally in the DWSIM. Okay, this is the viscosity routine from the steam tables property package. It comes directly from the steam table classes. We calculate the saturated liquid viscosity by giving the temperature of the stream, which is 75 degrees Celsius. Let us see how this is calculated. Okay, if this is already inside the steam tables class, if temperature is higher than the fusion point and less than the critical point, we are on region 1. Okay, so there is a small correlation here, and it will return the value of the liquid viscosity. Here it is. and the DWSIM gets the value and stores it in the material stream properties section for the liquid phase 1 and displays it to you in this table. Okay,